Hello, everyone in the Gemini control room.
Hello.
Hello, Jamaica.
Hello. I do wish I could join you this evening. I do apologize that I'm not there because I did plan to, but I am excited to join you virtually. Zach, maybe you can tell us a little bit about what's going on this evening and why there's so many people there. It's so exciting.
Yeah, so it's right now we're having a little bit of issues with GMOS, so you may hear some background noise. But we have a couple people who have joined us today. We have some members of the NASA Speckle team here, one of whom just left. And so they're here to work on one of our instruments, Alopeke, and they'll be speaking later on in the show about speckle imaging and the work that they're doing both here and at Gemini South. Okay.
Right on.
Perfect. All right, so you'll follow a vault for that?
Yeah, sure.
Okay.
The time was.
Okay, we'll go on. We'll go on. You're reselling? All right, you.
I'm on the target.
Okay. No, I think it's fine.
And so as we were just hearing, we have Brian as the observer and Matthias as operator. They were talking about some issues that they were having with GMOS and how to report them in the system. And I'll have them introduce themselves later when they're not getting set up for everything. But yeah, so it looks like we're moving on with the observing for tonight. So it seems all is normal right now, at least.
Oh, that's fantastic. That is absolutely fantastic to hear. And while we're just getting started, Zach, maybe you can introduce yourself and then we can catch everybody else later.
All right, my name is Zachary Hartman. I am a science fellow here at Gemini North. That means I just got my PhD a couple of years ago, and this is one of the first jobs I get post-PhD as a postdoc. And so my position is split between 50% of my own research projects and 50% of supporting observatory operations. This includes observing, so sometimes I sit in the chair Brian's in right now.
You steal my chair.
Yes,
More
like, and other times I help the scientists who propose for time here set up their observations within Gemini systems. And other times I serve on instrument teams. I'm a member of, well, I was a member of NERI, and now NERI has been retired. So
It's not far.
yeah, very, very sad day. And
Thank you.
I'm also a member of the Alopeke team here at Gemini. And you'll hear more from the two people here from the Alopeke team, as I said, later in the show. So, or later in the session. So, yeah.
Thank you for that introduction, Zach. We are so thrilled to have you as our guide and to liaise with the rest of the astronomers this evening for the session. I believe to your right, I see Steve Howell. Steve, hi, Zach. Hi. Zach, is Steve free enough to speak to us real quick for an intro?
Free?
I don't know. Are you free?
You're not engaged. I mean,
It's actually coin operated.
Yeah. Is it a little chocolate coins?
Yes, hi Jamaica. I'm so sorry you're not here in person. I'm so glad you're back though. Congratulations for having us, getting you back to Gemini.
thank you so much. I'm excited to collaborate with you all, and it is a thrill, especially to have you as one of the guests this evening, Steve. Can you tell us a little bit about yourself and some of the amazing things that you do?
Oh wow, that's like a great start up there. So hi, my name is Steve Howell.
We are locked in the back building. Call 2632.
Just answers the phone. I work at,
That's not for the audience, by the way.
yeah. Everybody call 23362, please. Just do. I work at NASA in California, and I'm here with my collaborator, Nick Scott, who's over there. And we represent the instrument called Alopeke, which is an instrument that in Hawaiian means fox. And it's an instrument that's on Gemini. And we are here this week to do some software upgrades to the computer on Alopeke. So not very exciting astronomy stuff this week, but very necessary things to do to our instrument.
Absolutely, absolutely. Well, that is thrilling, and we're looking forward to speaking with you and Nick a little bit later on in the session. Nick, if you'd like to introduce yourself, you are welcome to.
Sure. I'm on the Alopeke team. I help build the instruments, Alopeke and Zorro. That's been a few years now. I'm currently at the Chara Array. I live in Los Angeles. So I did a postdoc. So after I graduated in 2015, I did a postdoc, work with Steve at NASA Ames. I did 5 years there and then moved back to LA to work at Chara. So I specialize in interferometry. So it's either connecting small telescopes together to simulate one giant telescope that's spread out across a mountaintop, or what we can talk about later with Alopeke, a thing called speckle, which is where it's same principle, but all done within a single telescope. Mostly build instruments, do hardware, software.
Perfect, perfect. Well, we are certainly looking forward to hearing more about interferometry and especially as it relates to speckle imaging. And I will say for Zach, Steve, Nick, in the chat, we had Samuel, who is a homeschooled high school student interested in physics and space. So along with others in the chat, but Sam did put that there, and I just wanted to bring that to your attention because Sam, these are fantastic people to be connected with. And I know that you can find Steve online pretty easily. Nick, are you searchable?
NickScott.org, NICSCOTT.org.
Are you searchable?
If you search for Nick Scott, you're going to get like 200 other people with Nicholas Scott as a name. So,
okay, well, we will go to nickscott.org.
Yep.
Fantastic. Thank you.
Yeah. So go, Sam. Woo!
Yes, Sam. And to everyone, we are again thrilled to have you, and I see people are still joining. Welcome, welcome. We are excited to have your comments and questions in the chat throughout the session. And if you're just joining us, we are being well, we're just kind of getting started. Zach, who is Zach, can you wave for us? So Zach did an introduction a little bit earlier. He is going to be our liaison with all of the astronomers this evening. So working with us in the chat. And we also got a brilliant introduction from Steve and Nick, who are visiting with to work on the Alopeke instrument, which they will be speaking about later, as well as speckle imaging. So earlier, Zach said that the team was troubleshooting one of the instruments, GMOS. Zach, do we have an update on that?
Yeah, I think we're ready. I think we are moving on to observing. I believe we're on our first target. So tonight is what we call a MAROON-X night because
that starting acquisition.
All right. What was that? All right.
Starting acquisition.
Okay. So
We're doing science.
we're doing science.
We're preparing to do science.
Yeah. So it's what's known as a MAROON-X night, where we have a visiting instrument. It's called MAROON-X, and so on these nights we prioritize taking these observations because normally the team either takes the observations and or the instrument is on the telescope. And so tonight we're actually Gemini staff has started to become trained in operating MAROON-X. So we're starting to operate them, but it's on the telescope now. So we're prioritizing those observations. But we are still also taking our normal instrument observations using our facility instruments using GMOS and GNIRS. And I believe right now it is a GMOS observation.
GMOS observation, yep.
And so as you might have heard Brian saying starting acquisition, we need to acquire on the target. And so that requires a separate sequence from the sequence that we get all the awesome science from. And so Brian has started up that and is starting to acquire on the target, which can I show that screen, Brian?
Show them a picture.
Which yeah, show yeah, I'm not gacking right this second. We can, I mean, you can see the tuning star.
Yeah, you're on 5, right?
This is on 5. Yeah, it should be.
I'm gonna move this over here. So although that's not GMOS, that's GNIRS that's on there right now.
Right. So that was our tuning star. So that was to get
Okay.
our mirror and our AO system working. I'm just about to actually I'll just switch it now. So we just took our image.
Yeah, so in a couple of seconds, you'll see Brian begin to acquire on the target on the screen. Maybe. Or GMOS is going to be have some errors again.
Yeah, it says observe already in progress. Somehow it took a second frame without me asking it to.
Cool.
Yeah. It's in long slit, so this actually should be the observation that I wanted it. Just did it by itself.
But we may have to do some changes with GMOS again because it kind of had an error. So we'll see what happens with that.
So GMOS is your multi-object spectrograph. Can you tell us a little bit about its wonderful capabilities, Zach?
Yeah, so GMOS is really the workhorse instrument here at Gemini. It has a lot of different modes, and that makes it the most popular instrument at both Gemini North and Gemini South. There are identical copies of it at both sites. It is a imager. It is a long slit spectrograph. It is a multi-object spectrograph, and it also has a integral field unit in it as well. And so it can do all these different modes, and that makes it very valuable to a bunch of different astronomers around the world who want to use its capabilities. And so there's an image of one GMOS observation, although Brian is currently acquiring on it for a GMOS long slit observation.
We're gonna have to restart the acquisition sequence.
And we're going to have to restart it again. So GMOS is a very powerful instrument here at Gemini.
And you mentioned that Brian was taking a long slit observation. Are there short slit observations also?
Good question.
That's a great question.
I mean, technically multi-object spectrograph, right? I mean, those are short slits, but traditionally no. So long slit spectroscopy is just you basically have a metal or some blocking sheet that has a slit in it. And then that slit you center the slit on the star, you let that starlight in, and it gets filtered through an instrument to a grating, which disperses the light across different wavelengths. And then that eventually goes onto the CCD, and we can look at everything, which hopefully we will be able to see as long as GMOS is working today. So yeah.
Can you tell us what that bright blob is that we're looking at, Brian?
Well, in general terms, yes. Okay,
Yeah,
so this,
you don't have to be specific.
so I don't know. Did we do the intro to Gemini North, like what Gemini North is, Jamaica, and like the partner countries and everything like that?
We didn't do that because Zach said the volume was a little low, was
Okay.
quiet, so I didn't do it.
Okay, so
think
yeah, so Gemini North and Gemini South are telescopes that anybody in the world can apply to. We have a number of partner countries, but if you apply through the US, anybody in the world can apply. So we're taking an acquisition for a scientist in Korea now. And this person in Korea is interested in looking at active black holes. And they want to take up. So actually, when we're looking at really distant things, generally they don't change very much. So galaxies that are very, very far away, they don't change a whole lot on human timescales. But black holes can. And so we're actually taking observations almost every month of the same black hole, and they're interested in seeing how it varies in terms of its brightness and what that means about the accretion dynamics. So the gas flowing into the central regions of this galaxy, which hosts this black hole, how that gas comes in and how it excites the black hole. So that's the basic principle, I think. This is not my science. This is not, so I'm simply an observer here. But that's what this blob is in the center. So this is the galaxy that hosts the black hole that we're about to look at. I hope we're about to look at.
That's pretty cool. So that thing has a black hole in the center.
That's right.
Can we see the black hole?
If we take a spectrum, we might be able to see it. Yeah.
Cool.
Yeah.
All
So
right.
hopefully we can get to this. So right now this is just an image, but as I think Jamika and Zach mentioned, so we're going to try to take spectroscopy with a long slit, and that's going to break up this image into thousands of different colors, and so you'll be able to get very precise information on the source, and you'll be able to see all sorts of things about the rotation of the gas and how much like outflowing gas there is and how excited the black hole is. So that's what we're going to hope to do.
Fantastic. We are so thrilled to be along for the ride to shadow you all as you take your observations this evening. And black holes are certainly really exciting and still a bit mysterious, right? Have we
Yeah, so Jamika, you'll just hear me like so Mateus and I'm controlling the instrument, and Mateus is controlling the telescope. So it takes two people, at least two people. Actually, it takes an entire hundred, a lot of people to and in fact we have our day crew lead here as well. Thanks. But in the control room at nighttime, usually two people, one controlling the instrument and one controlling the telescope. And so we talk back and forth. Mateus just moved the telescope for me, and so now we're going to see if we're centered up on our source. So that's what, if you hear me talking, that's what I'm doing, or I'm muttering to myself, one of the two.
Thank you for the clarification.
How do we know the difference, Brian?
Yeah, I know. I can't help you in that guy.
Yeah. See that? Yeah. Can you point that out?
I wish.
You get a picture of that?
The problem is on the online thing, it's only showing the north and up.
Yeah. It's on the previous one.
That was good timing.
Yeah. It was the Geminis this week.
Yeah.
Yeah. Appropriately named.
Yes. The Geminids, I think the peak is what, Wednesday, Thursday?
Here in the back building, thank you.
Yeah, we just saw one on the all sky camera over here.
Oh, wow.
Yeah, sorry, we tried to show it to you, but we couldn't do it, but there was a nice one we got.
Don't worry. You know, I'll put a link to the all sky camera to some of the cloud cams in the chat, Steve. Thank you.
So I'm setting small up for this. And we're ready for science. Yeah. Let's do some science.
It's like an echoey voice.
Science.
Yeah.
Brian, when you get a chance, there is a question from Peggy. Peggy Lavelle. Welcome, Miss Peggy.
Hi, Mom.
Is that really your mom?
It's really my mom, yeah.
Is it really?
Miss Peggy is absolutely wonderful. I've had the pleasure of meeting her and having a good conversation with her multiple times. So welcome, Miss Peggy, and Brian or Zach or Steve, or to anyone in the control room.
Oh, there's no way anybody but Brian's answering this question.
Yes, I brought dinner, Mom.
Well, her question is actually about black holes. The question is, why do black holes change more frequently? Or why do they change frequently?
Starting science right now. So this question for me.
Yeah.
Okay. Good question, Peggy Lamo. Basically, any any accretion event onto a black hole. So as gas inflows to the central regions of the galaxy, which is usually where a black hole is, at least the very massive black holes, the time scale is quite short because if any small accretion event occurs, there can be flare-ups from that black hole. The gas can heat up very, very quickly, and that can happen on a very, very short time scale because there's a massive gravitational well there. And so the accretion energy that's released is quite immense. And so things like, I mean, same thing for like a supernova, for example. Stars are relatively steady for long periods of time, for tens, hundreds, thousands of millions of years. But then when a supernova occurs, things can happen very, very rapidly. So gas dynamics change, pressure and gravity go out of equilibrium, and things can happen on timescales of weeks, days, hours, minutes, seconds. And so the same sort of thing with a black hole is that generally they can be fairly stable. The one in the central regions of our galaxy right now is fairly stable. But when things go out of equilibrium a bit, things can happen very, very rapidly.
Okay, thank you so much, Brian. Ms. Peggy, I hope that was a sufficient answer. And if you require additional details or anyone else, please let us know. And
You know where to find me.
Yes, she does. And I'm going to drop the link to some of the NORAD press releases and that relate to supernovae and black holes, because there are certainly a handful.
There she is. Hey, Peggy.
Did we lose Tamika?
Yeah, that's what I'm wondering.
Nope, nope, you didn't lose me. I was just on a different screen.
Just talking to the real scientist about another screen.
Yeah, fact check.
Fact check that black hole thing. So you need like a roving camera.
I mean, that's technically that.
Yeah, but you need something where you could like go look at the schedule thing. Go
Just
look
put it on a
at
Roomba.
So part of the reason we do this, and part of the reason it's set up this way, is because the PIs have priority over their data, and we have concerns over showing too much information. And so you can.
Yes, I completely agree with you, Zach.
It is the way it is, and we have to work around it. And
Fair
so
enough.
you won't be seeing any RAs or decks on any of the targets tonight.
Yeah.
But that's just the way to protect the PI's privacy and protect any data that we get from it.
As well as the UAPs.
Thank you for explaining that, so that our those who are joined us can understand why we we're seeing something different tonight than what they would see when we are observing, say, with Lick Observatory, or with someone, or with an observatory where they're doing classical observing. So I appreciate you sharing those insights. And you also mentioned RA and DEC, right? Ascension and declination. For those who in the audience who may not be familiar with those terms, Zach, could you explain those?
Yeah, Brian, I think gave a great explanation of it last night. Although we're looking at a spectrum right now,
Ooh.
if we want to focus on that, this is of that black hole. But in brief, unless Brian wants to say his explanation of it, I mean, right ascension and declination are the coordinate systems astronomers use to point to stars in the sky. So every point in the sky has an RA and a declination, kind of like longitude and latitude, but for the celestial sphere rather than the globe.
Yeah, not clear. There's some stuff right there. That might be. It's hard with the night sky.
They're currently staring at this
And there's a
spectrum
detection.
intensely.
That if it's emitting or not.
Yeah.
Yeah. Have to change the stretch. Yeah, pretty cool. But yeah, there's something there. Something there, yeah. Just continue them anyways.
Well, we could hear you saying that there's something there.
There's something there. It's very exciting.
Are you on the? Oh, you're on the screen. Okay.
Yeah.
So, so this is our first science observation with GMOS of the night. So before we were taking observations to get set up on this target, and now we're taking the actual spectrum. And I have to actually check how it's going. We're getting close to being done. No, actually, we're okay. And so we've now taken two spectra at two different locations. Let's see, hold on. Just change for me. Yeah. Yeah, so we're going to be taking 4 total spectra. Each observation is 1.5 minutes, and we're going to be moving our slit up and down so that the black hole appears in different locations on our observation. And then the person who proposed for these observations is going to take all that data, combine it all, look at the constituent light emitted by this source, and then they're going to determine why it's doing what it's doing. So that's the plan. That's the plans. They probably have some suppositions as to what they might see, and then we're gonna test. They're gonna test those suppositions with these data.
So before we go on to something else, I just wanted to give the other people in the room who haven't introduced themselves, seeing as we're kind of at a low point as we're just taking data. So
Hey, this is a good part. This is what we got.
I said a low. I said low point. is what I meant. Is what I was supposed to come out of my mouth, but you know. So Andrew, do you want to introduce yourself? Or?
Yeah, I'm Andrew Galvin. I'm site manager. I manage the paint crew. Much less exciting job than science, but we turn wrenches, bolts, do installs, maintenance, all throughout the day, so that they can hand it over and provide all this lovely science for the world. So, yeah.
Yes. So, I mean, one thing we should point out is that right now we're at a nice, comfortable altitude in a nice, comfortable room. It's going to get freezing here later tonight, but we're at about 300 feet above sea level here. And Andrew, I mean, every day basically, right? Like,
Yeah.
I mean, you're either down here managing people up there, or you're up there yourself.
Up, down.
Yeah, 14,000 feet. So, I mean, Gemini, we don't observe at nighttime from the summit. There are telescopes in Maunakea that where the operators, observers do that. We have the luxury of being here. Like, I'm 2 minutes away from my house right now. So it's amazing technology that we're able to, the day crew does an awesome job. All of our engineers during the day do an awesome job getting everything ready for us at nighttime. So it's nice and comfortable in here, and that we can actually do the science that everybody in the world is asking us to do. And so, you know, it's a, as I mentioned earlier, it's a huge set of people, both, you know, here in Hilo and our sister site, and within the Water Lab community, and all the scientists that propose and make, you know, Gemini worthwhile. So all of these pieces have to work for us to be able to do the low point, as Zach put it. I'm completely joking.
I'm never gonna live in that.
But they go up to 14,000 feet every day, so that basically we don't have to. And so that we're nice and kind of fresh for the evening time. We drink our coffee and press our keyboard buttons and do the science.
That's
So I just want to put that out.
amazing. No, thank you for sharing that. And so, Andrew, is it typical that you drop into the control room for evening observations after being at the summit during the day?
I try to do it every quarter. It's been hard lately, but yeah, I was dead set I'm gonna do it this month. It's gonna happen. So yeah, today it just kind of worked out where I had a kind of a sort of chill day. I wasn't so totally mentally exhausted, and I could just drop into Hilo and then just drive out. I'm gonna be working from home tomorrow, so because I got an hour and a half long drive back home after this. But yeah, no, that's fine.
Well, we appreciate you joining us for tonight's session and for sharing with us a little bit about what goes on during the day. So if we can continue a little bit, Andrew, the day crew consists of what is it all engineers or are there different technicians that make up the day crew?
So the day crew's primarily made up of technicians that go up there daily. We work 10-hour shifts. So some folks do like a Monday through Thursday and some folks do a Tuesday through Friday. So there's always coverage on the weekdays. Engineers are up as needed. Typically, we do have dedicated engineers that come up 2 days a week. We also have a safety coordinator that tries to make it up there 3 days a week, but his time is shared between Hilo and Summit. But yeah, that's always something to do up there. Always something, either short-term projects, long-term projects, something breaks down. Faults we need to get after. Always.
We saluted
Always
3861.
I can tell you a little bit about what we were doing today. So we have the dome itself rotates on 38 rollers, and they're about, I mean, what you would expect to be on like a freight train, and they all go around a circular track. So today we have a troublesome wheel, which we call a bogey 38. It sets on leaf springs, so there's some suspension there. Each bogey has like some suspension. Well, they also have bolts that kind of like tip, tilt, yaw as they go along the track, and one of them is kind of out of alignment. So I don't know if you'll be able to hear it on camera, but whenever we're slewing the dome, it does make a little bit of banging. So tons of force is happening in the air on the dome. And so it's actually like sliding on the track with, yeah, I can hear it right now, actually. It's being noisy, it's singing. So right now it's like a couple of tons of force knocking it this way, that way. It doesn't know which way to go because it's out of alignment. So that's something we're going to address tomorrow in the next 2 days. And so each bogey is probably like 1,500 pounds. I mean, it's just solid steel, you know, rolling around. It's still making noise. I hate that noise. I really do.
So you can actually, from where you're sitting right now in the control room, you can hear what's going on in the dome on the summit?
So behind me, there's basically just a regular old security camera. It has a microphone on it, and as they turn, even though it's completely dark, I can still hear it. So I know you're turning the dome.
Jamaica, were you gonna go outside and see if you could hear it?
No, I knew that wasn't going to work this time, Steve. Wow. Andrew, is there I know that Gemini does tours at the summit now, which is exciting that those are back. Does the day crew interact with people who are on the tours?
We try not to because there's a lot of work that's usually going on. Myself and Sean Anderson and Peter Michaud and Joy Pollard are usually the ones kind of facilitating that, as well as Linda Williams, who's new to our team. But if we can time it out right, we can do end of day checks for the tour, which is basically they stand off to the side And we slew the telescope down and pick a couple of targets and it's so cool. Some of them get motion sickness because the dome is turning one way and the telescope is turning the other way. And I tell people, you're looking a little pale, you need to look at the floor. Please don't barf on my nice, clean level 5. Please, yeah.
Don't make me stay longer.
No, it'll freeze to the floor.
That's right.
That's not fun.
And then when it warms up, it's like,
Oh, yeah. No, we're all trained in emergency response as well because people are not used to 14,000 feet. So, if we have a medical emergency, we are the responders. It's gonna take an hour for to get an ambulance up there. So I usually have myself and Sean pal around, just make sure everyone's okay. We have oxygen for people. Everyone's different. Everyone reacts to altitude differently, especially if they have like ongoing health issues. So, we just want to make sure everyone's safe, comfortable, not sick. Because,
And so that drive to the summit and back down that the day crew makes daily, how long is that drive? Just to give context for those who have not had the privilege of visiting Mauna Kea or the summit.
So from Hilo to the base station, it's about 40 minutes.
Maybe
And we stop there and we spend at least 30 minutes acclimatizing. That's from 300 feet to 9,000 feet.
100.
Spend 30 minutes to acclimatize. And then you travel the rest of the way up, which is another
they're probably local.
20,
Yeah, that's a serious
25
line.
minutes.
Yeah, it's probably H alpha
roughly
M2
to
S.
the actual
Yes,
summit,
right.
which is,
Cool.
13,860 feet to be exact. So it is quite a drive. It's a lot of time sitting in a vehicle, but it's really the only way you get out there. And whenever there are blizzards, icy conditions, we do not venture up there. Try not to at least. Yeah. We need the zip line. So from the summit to Hilo. Straight shot. That's a straight shot, yeah.
You probably selling tickets on that thing.
I think some people don't realize that we actually get snow. And in fact, there was snow on the mountain, I think last week. I saw some vestiges of the snow over the weekend, but we think we have a good covering of snow last week. So if in the off chance that happens overnight for some reason, how do you all deal with that?
I can tell you the Alopeke run dealt with it by we received no data for a week. That's how we dealt with it.
No.
Bad weather is not good for astronomers.
That's true, of course.
But can the public look at the summit camera images?
Yeah.
Should be able to, yeah. There's still a little bit of snow.
Yeah, so Jamaica, if you put the link in for the summit images and people look about 2 weeks ago.
Oh, yeah.
There's some great shots of Maunakea just covered in blizzard.
Oh, wow. Okay.
Starting acquisition.
Yeah,
Oh,
that's pretty fun.
I think last year it was about 4.5 to 5 feet high of snow. At the highest. Yeah. So, yeah. They have an entire dedicated road crew that actually plows out the snow. Big old graders.
So now we're getting a P2 bolt.
Yeah.
And we're on OI.
Yeah.
Oh,
Big
that's
problem.
Andrew. They do have the facilities crew there on the mountain that deals with keeping everything clear.
Yeah.
And we have another question in the chat for anyone. It's from Miss Peggy Lamo. How long in general does it take the body to adjust to the oxygen level at the summit?
I can answer that one.
Yeah, please.
Yeah, I'll answer that one.
20 years.
So 20 years.
It's
goodness.
a phase 2 error.
Okay, so there's not a lot of research or data on people who go up and down extreme elevations, daily. But I can say from personal experience, for me, it took me about
Yeah,
a
and
month
the
to
act with
be
the OI, it's OI.
okay
Yeah.
going up there daily. I had migraines. I was very not happy. It took a while. But everyone's different. Everyone, like I said, everyone reacts differently to altitude. For some people, they're fine. For some people, they never get over it. I have some engineers that go up there and they are on oxygen all the time, even though they come up there all the time. But it's just your body, you know.
Should work. Should work. Same
Yeah.
one.
Thank you. Thank you for sharing that, Andrew. And I think that it's something that many people don't realize. And you mentioned earlier that you, when you all go up, that you stop to acclimatize for at least half an hour, so that you can be more level-headed when you get up, but also so that you can be more aware of how your body is responding once you're at those higher elevations.
The altitude does really, really fun things. Like some people just burp continuously because there's like they're effervescing all the nitrogen or something. It's different. Very interesting. Yeah. I know I have a crazy appetite. I don't know why. I tell bad jokes. And tell bad jokes all the time. That's all.
Oh wait, I do that a low altitudes too.
And so, Zach, as we're looking back at, there seems to be still spectra there.
Is that what it is? Yeah, there is a spectrum up there. It's the last one from the previous observation. We experienced a error with with the next target, and so Brian is fixing that error, and we will be going on to the next target shortly, which is, I believe, from the same program. And so we're going to be looking at more black holes. And so hopefully in the next couple of minutes, we'll see that more spectra, another acquisition sequence followed by more spectra.
Okay, we're ready for the action, Zach.
Okay, nice. It cleared. So that was a phase 2 error.
All right, so it sounds like we are taking the data.
A1! A1!
We need to redo that step. Loops were open.
Okay.
So
The loops are open, really?
Yep. We're open because I need to listen to clean the error of the video. So they open.
Oh, you had to clear the error, but I stopped, the loop stopped on
No. I opened them.
Oh, you opened them. Okay. All right, so we gotta do one more time then.
But I'm kind of letting them talk. But yes, as Steve was pointing out on the spectra, you can see a lot of different things. Although I can't change any of the scaling because it's all on. There we go. Now it's changing. So you can see that in the middle you have an example of one of the spectra. Is this an arc?
No, this is the source. Actually, so
Okay,
that's
this is the source.
that'll be the skyline, and then the trace of the target is in the middle.
Right.
And that's probably a broad emission feature there.
and as Steve was whispering in my ear, that bright source at the center of the spectra is H alpha. So
If nothing else, people that watch this will know why all the conspiracy stuff is junk. Because getting scientists to keep quiet is really hard. Yeah. Don't shut up. We'll just keep saying, what about this? Oh, have you watched this thing?
You know what? Yes, it's too late. Yeah, we're gonna have to move on.
So you see the center spectrum. You see some cosmic rays and some dead pixels kind of floating about on the spectrum. Those are just those weird marks on that don't seem to correspond to any of the lines. And then you can see some of the skylines going up and down, covering the full width of the width of the image. So yeah, it sounds like we're going to be moving to a new target, which is one of the things at Gemini that we do frequently is because we are a Q observatory. So we have a schedule that QC coordinators make during the day, and then
Cal 20150, please, Matthias.
observer and the operators take the schedule and run it to the best of their ability. And the Q coordinators make a bunch of different schedules depending on the conditions. So it could be super cloudy, but near perfect seeing, or it could be the other way around, or it could just be perfect, and everything is great. And I think that's what tonight is supposed to be.
Great. Like somebody
really good. Although I'm gonna knock on something. And then so what happened was we had this error with GMOS, and so we spent a little bit of time on it, but because of the queue, and because we have more important observations further in the night, we had to move away from that observation that we were going to take, and we were moving on to another one. And these programs have rankings based on a bunch of different criteria, namely the scientific ranking that the national committees that are put together to rank these proposals give them. As Brian mentioned, Gemini is an international observatory, so we take all of these different proposals from all of these different countries. We receive them as a ranked list, and then we here at Gemini put them together into some schedule, and then we try to execute as many of those observations as possible. And so what you're seeing here tonight is significantly different than other observatories where, for example, Lick, if you've been on one of those sessions, where it's classical, where it's a single team or person who's taking an observation of a specific program. Here we're observing a bunch of different programs for a bunch of different scientists all over the world.
So Zach, just so you know, we're moving on. We're actually changing instruments to Maroon.
All right. So now we're changing.
You're welcome to show that screen if you like.
Yep.
And hold on, let me just, okay.
All right. So now we're moving on to MAROON-X, which is a high resolution spectrograph here at Gemini North, and is principally used to go search for planets around other stars. And if you want a really great discussion on MAROON-X, please check out our previous Shadow of the Scientist session. Whenever it gets on to YouTube, or if it is on to YouTube, check that out, where we had Madison from the MAROON-X team joining us and giving a great discussion on that. But this is also, I think, a good point to bring in Steve and Nick, because Alopeke does a lot of tangential work related to exoplanets. So if you two want to kind of explain Alopeke and its role in exoplanet finding and beyond, critically beyond, and take it away.
Sure.
You can start, Steve.
Oh, thank you, Nick. All right, so this instrument that we've been calling Alopeke, which is Hawaiian for fox, is a twin instrument, much like the twin Gemini telescopes, with an instrument at Gemini South called Zorro, which is Spanish for fox. So we're very clever in our naming conventions. And they're instruments They're instruments that are about the size of a carry-on suitcase, if you've been flying lately. Instruments like MAROON-X are about the size of a small Volkswagen bus or something like that. So our instruments are very tiny, and they are permanently mounted on the Gemini telescopes in a very tight-fitting little region. And what they do is they take images of stars mostly, and they take images very fast, of order of one image every 50 or 60 milliseconds. And they take thousands and thousands of images, and each image looks like a bunch of dots or speckles. So the technique is called speckle interferometry. And you mathematically combine all those images using a mathematic technique called Fourier analysis. And you end up with an image of the sky that gives you a picture that you would get if your telescope was outside the Earth's atmosphere. So you remove all the blurring of the Earth's atmosphere by using these mathematical
Okay, take a
techniques.
5-minute science.
So we use that a lot to stare at stars that have planets that orbit them, because many of the stars, something like half of them, are actually two stars that orbit each other. And then you have to figure out which of those stars the planet actually orbits. And you can do that by using our image of these two stars. So it's a cool technique with a small instrument that's mostly done in software.
Well, it takes advantage of a property of light that light's a wave. So the light comes from the star, it's a perfect wavefront, it's just like a ripple across a pond, and then it gets our atmosphere and it gets completely messed up. And that makes this really nice, wonderful 8-meter telescope without adaptive optics and without speckle, function like it's something you could buy for $50,000 or so. Like a big Dobsonian telescope, and you have to do clever things to take advantage of the properties of light. So with speckle, that photon gets messed up in the atmosphere, but a little bit of the wave overlaps with other ripples, and that causes interference. This is where interferometry comes from. It's the interference pattern of the waves of light. And by doing a whole lot of math, you can back that back out and figure out how the photon interfered with itself. And from that, figure out the size of the source and as if there was no atmosphere in the way. And what we get from Alopeke and Zorro is about the equivalent. It's a theoretical maximum resolution of Gemini, which would be about equivalent to if you're in Los Angeles, being able to see a car in New York City. About that size.
That's incredible.
We think so. Thank you. Thank you, Jamaica.
Absolutely, absolutely. Wow. And so Nick or Steve and Steve, do you have a paper that we could, if you give me a name, I can drop a link in the chat for everyone to maybe follow some of the research that you all are doing with Alopeke.
It's twin speckle. I'd have to Google it. The latest instrument paper I'm the first author on. It's at nickscott.org under my CV. You'll be listed there. It's twin speckle imagers for Gemini, I believe. Something like that. From I think 2018.
Yeah, that'll tell people all about the instruments and the details and
brutal, painful detail.
But I mean, one of the things that Alopeke has in terms of papers and stuff like that is there are a lot of binary papers looking at it or using it to look for binaries or follow them.
Why do astronomers care about binaries?
I don't know. I'm trying to make this argument and they just throw it away. So, but
the only way to astronomers you'll hear talk about binary stars a lot or multiple star systems. Why do we care about so much about those rather than single stars? Well, most of the stars in the sky are binary or multiple. So about half are binary, about a quarter are triple or more. And the way the physics works out is very basic, undergrad level physics, that to measure the mass of something, how much stuff it has, you need, one of the best ways to do that is if it's a binary, the way it orbits directly tells you the mass of the stars. So it's a way for us to weigh the stars, figure out how much stuff there is in there. And then couple that with the light we're getting, the spectra we're getting, you start learning a ridiculous amount of information about stars, all just from the light we're getting.
And so, for example, if you go out and look at the night sky, you see a bunch of stars. Over half of those you see actually have very close companions, and those two stars are orbiting each other. But you can't see those companions because they're so close to a very bright star that your eye or even a large telescope alone cannot separate the two stars. So that's what our instrument can do. And we can study stars that nobody else can really see. So. We also do things like imaging winds from stars, imaging disks around stars, Zach, for example, has a great program looking at stars that are very old in the halo of our galaxy and how did they form and are there many of those binaries as younger stars? So all kinds of fun science is done.
Incredible. So I've dropped, Nick, I have your webpage there in the chat for everyone to check out. I was looking at everything that you had on your page, and there's under ResearchGate, you have quite a few papers, very impressive, but I couldn't quite find the one that you were pointed me to. So they can just go find it for themselves. But I'll keep checking. And that was a great segue to you, Zach. Zach, so you're doing work characterizing the stars in the halo of the galaxy. Can you maybe tell us the difference between the halo and maybe the arms of our galaxy?
Yes, can you slew to 202.123, please?
Hang on, Zach has a little task he's doing right now.
I've been tasked for something, so give me 2 seconds.
We gave him a homework assignment. Hang on.
Yeah.
I have a laptop on it.
All right, I got it. All right. So yeah. So
Well, it's 2021. That's why I gave you the wrong year.
Yeah.
oh well, your SPIE
18
paper.
was messy, I think.
2021. Here, I'll send it to you, Zach.
I got it. And there. All right. So yeah. So I mean, when you look at our galaxy, you typically, I mean, if you go to South America, or if we're really lucky from here, you look up in the night sky and you see the disk and the bulge of our galaxy across a large portion of it. But there's more to it than that. So in the disk and the bulge, well, really in the disk is where you have a lot of stars forming. There's a lot of gas and dust that is forming a lot of stars right now. But the galaxy hasn't really always been that way. And so there's this diffuse halo of stars in the galaxy, some of which were born in the Milky Way and were maybe even formed in the disk of the galaxy, and then were kicked out through some interactions into the halo. Other stars were accreted onto the Milky Way from early on or midlife of the Milky Way as we know it, from galaxies that the Milky Way has kind of eaten. And so you have these old metal poor stars that are floating around out there, and they are drastically different from the disk in terms of their formation and their potential properties. And so we don't really know a lot about them. And so my work has been going out and studying the binary population of these systems and really digging into, okay, how does that binary population compare to the disk that we see everywhere? And it's harder than it seems because a lot of these stars are fainter than disk stars around us. And so you really need Gemini and Alopeke and Zorro to really dig down and find these faint stars.
And thank you for that link to the paper that Nick was referring to earlier.
And so, Jamaica, you heard Zach use the term metal poor. So a fun fact that astronomers have their own periodic table of the elements. So if you're a chemistry fan, you know the periodic table of the elements has
Give me a PL set of
109 elements or something like that. Astronomers have 3 elements.
P
They have hydrogen, helium, and metals. That's sort of the lingo in astronomy. Because hydrogen and helium make up so much of the universe that everything else is just so small by comparison. We just kind of lump it all together in metals. So there's a little fun fact. If you're studying for a chemistry exam, don't use that fun fact because you'll fail. But if you're studying for an astronomy exam, you can use it.
You actually took the question out of my mouth because I was gonna actually ask that, ask for clarification. Yes, because I think that's absolutely fascinating that when astronomers talk about metals, it's kind of clumping everything together. That's not necessarily what we would traditionally think of as metals. So
That's true, yeah. So for us, even krypton is a metal.
And we have questions. Let me come back to the chat here. Actually, several questions. First, are there any rules about data being shared, or is it actually up to the PI to determine if their data can be shared and when?
Yeah, it really does depend. I mean, there are some
funding source too.
When in doubt.
Yep. It depends on the funding source. It depends on whether, the PIs are very secretive, depends on whether the subfield of astronomy they're in is very competitive. And so, I mean, so for Gemini, all of the data taken here will be public within a set amount of time. There's what is known as a proprietary period, and I believe it's set for 12 months. 8. Okay, I thought it was 12. But the chair of the board has informed me that we've tried to make it is 18 months
left.
And so after 18 months of sitting on the archive, the data will be public and anybody can go download it. So you can go to the Gemini archive right now and download any data that was taken before or after 18 months ago. And so that's a really good resource for people, in particular if someone has this really awesome idea and they go look on the archive and they're like, oh, this data has already been taken on it, but it was used for something completely different. So I'm going to grab it and use it for my own data or for my own purposes. So it really depends.
It's a weird balancing act, right? Because scientists, most of us want data to be completely open and public for anyone to access at any time. But then if you're the person that built the instrument, or especially if it's a student, you want to give them time to write papers, to get their name out, to actually get a reputation and do something. Yeah, and graduate. So most places have a proprietary period. But like going to public data is great because like Eris, the Trans-Neptunian object past Pluto, was on photographic plates from the 1920s. Like it could have been found way before it was in late 90s, early 2000s.
Yeah, this is an ongoing debate within the astronomical community because I know for several of the large upcoming surveys, they are having open debates about how much proprietary time do we give people. I know for JWST that was a big topic of discussion.
And it gets harder when you have more and more big teams. So it's fewer and fewer of the small groups of a handful of scientists. Now you've got a paper with 100 co-Is.
I have 13.
Calling dibs on data.
Yep.
Yeah, I definitely understand why there would need to be a proprietary period, and that's really good to know. It really is.
49.
Total. Okay, thanks.
And so now I have dropped a link to the Gemini Observatory archive, Zach, that you referenced. And so is that pretty easy to just kind of search and use and find data that, like if I were a student, I am a student, but if I were looking for particular data, how do I use the archive?
It's yes and no. If you know a little bit about the target, if you know it's RA and DEC, you can just plug that into the archive and it will show all the observations taken within, I think default is 2 arc minutes, so 60 arc seconds, or what is 60 divided by 3,600? I don't know. A really small amount of degrees. I can't do math right now.
Whip up my phone, the calculator.
Yeah, I can't. It's been a long day, so I cannot do that math on the top of my head right now. Or if you know the target name, you can go check that out.
To 109, please.
with a little basic knowledge of the target, it should be relatively easy to find data on the archive.
So for example, in this web page that's up here,
And
if
so
somebody
I,
went, if
Yes.
Jamaica went to target name and typed in Jupiter, and then did search,
Conceivably, something will show up.
Yeah. then over to your left there, Jamaica, in kind of the middle. Left there.
There.
There you go.
Hey. And so as you can see, there's some proprietary data,
Well, thanks.
but you have a record of the data that is available for this target.
okay, so it looks like everything is listed proprietary, but we can click on some things.
Like there's not enough Jupiter.
Yeah.
You'd think we'd know about it by now.
Yeah, so if you scroll down further,
Keep going, you'll eventually get that.
maybe eventually.
Does the audience know about its files? Not open.
Well, that's what we're about to find out.
DS9's free.
I wonder if,
Filter out proprietary.
yeah, if you go up, all the way back up to the top.
The date rate.
And Matthias, can you?
Yeah, that's what
Offset of 4, please.
if you put like, I don't know, into the UTC date on the left-hand side. If you put like 2000 0101 to 2019 0101, let's see if it grabs anything.
Okay, tell me that again. 2000.
0101, basically Joe, from January 1st 2000 to January 1st 2019. We'll see if it grabs anything.
Okay. So that was 2000 01 to, you said 2019?
Okay, Matthias, I'm
01, another 01 is needed, I
Science.
think.
Really something.
And then dash,
Holy crud.
and then 2019 01.
Yeah.
Yeah.
98.
98, I want to say.
Does that look like that?
Yeah, put another 01, put another 01.
Got it.
All right, let's see if it grabs anything.
God, I remember seeing that as a kid.
Yeah,
That was
I'm betting Gemini looked at Jupiter then.
Yeah, I bet.
I was in Alaska when that went off.
Ooh.
There we go, there's some data. So now you can see there's a little bit more info. You can now download the data on the left-hand side instead of the giant proprietary thing.
So can I click on one of the files?
Sure.
I don't know whether clicking on the files itself will download it,
Try it.
but yeah, try it.
Okay, let's try that.
Can happen.
This is science. Poke it and see.
What's that button do? What's that button do?
Oh, that's interesting.
Was it purple before you poke it?
Oh,
Hey,
All right, well, this isn't really what we wanted, but
come on, it's a
it's
fence.
it's a header. It's the header. I don't think it has. I think it's just the header. I don't think it's. I don't.
Flexible image transport system.
It looks impressive, whatever it is.
Yeah, keep scrolling, Jamaica. Wait till you see the data. It'll come up
No,
eventually.
it's just the header. It's just the header.
Oh, just the header?
Yeah.
it's
So
just-
this is. So astronomers use a particular kind of file for all our data, which is called a FITS file. And so this is this should be on any astronomical data that is ever taken. And it contains a lot of information about the target. So you can see, you can just glancing at everything here, you can see the target name, you can see actually the observer of that target, you can see the instrument that was used, where it was taken, its Orient deck, its epoch. So this contains a lot of useful information for the data reduction when you process this data.
If you're a graphics nerd, it's a FITS file is a TIFF with the header.
Oh.
Oh, okay. It's a TIFF with a header. Okay.
That's a lot easier to understand.
Oh, wow. Okay, so I'm going to close this and see. So we have data label, UTC time, we see the instrument, and then we have some more data, waveband, binning, and a few more things over here. So if I were to click on, I'm trying to.
In the chat
Yeah.
said you click the D on the left.
Yep.
Hmm.
I don't think clicking the object does anything.
No, it did. You're right.
It may sort it actually is what it did, I think.
Oh, okay. Okay. I'm gonna stop my share now. All right. That was exciting. That's exciting to kind of go through the archive, and certainly Sam and anyone else, Yuli as a teacher that we have who's joined us this evening for this session. Please feel free to go through that archive, check it out, explore it, and if you have any questions, definitely let us know. You can email me and I will pass the questions along for sure.
Open this file. The program is called DS9, like the Star Trek show. So if you Google not Star Trek DS9, SAO DS9, you can download the program and open bits files.
Okay, and here is a tutorial. Well, actually, let me just have the link that Nick was referring to. Just a moment. Okay. Okay, so I will add that in the chat. And so, Zach, what do we have on the screen? It looks like we have a blue spectra and a red spectra.
Yep, so this is MAROON-X spectra, and so on the left is the red spectra, on the right is the blue, I'm assuming, unless they flipped them. And so you can actually see the, oh, I can't control anything on that screen. You can actually see the different spectra, well, not the different spectra, but the, oh, we're changing, sorry. You can actually go in and see the different orders of this shell spectrograph, which is basically it's the same spectra just split into different wavelength bands and stacked on top of each other. And if you look really closely, you can kind of see some of the absorption lines in there, which are the dark areas in the, oh, there we go, Brian's zooming in, which are the dark areas in the spectra. And then the rest of it is continuum. And so what the astronomers who look at this will do is they'll look at those absorption lines, compare them to a star for which we know the rate of velocity, and they'll see how the lines shift over time. So these are a lot of the MAROON-X observations have a lot of epochs, and so they're taken a lot of times over the course of a month or several months. And the goal of this is to see how those lines move. And from that information, you can determine a lot about the parameters of the planet and the star in the system. And so we're right now looking at one of our MAROON-X targets. And I believe we're on here for a little bit.
Yeah, so we're observing right now a 30-minute frame on a nearby star. And so this is a long-term program. This is a LP program. So this goes over multiple semesters, and this is definitely not my science. So I don't know what I'm talking about. But from what I understand from a cursory glance, is that they are picking out stars in the local neighborhood. So within, I don't know, 20, 30 light years, I don't know, something like that. So bright stars, fairly bright stars, some of the brightest stars in the sky. And we're pointing MAROON-X at them, and we're trying to determine if there are planets in the circumstellar habitable zone.
Or if there are planets there, we're trying to figure out their properties.
Exactly, yeah. So it's a planet search Number one, look for planets. Number two, what are they made of? Number three, are they in the habitable zone? Number four, profit? I don't know.
Is there life?
Is there life? Yes. Yeah, sorry, not profit. Is there life? Yeah.
Is there life?
Yeah. And so I think Bernard star is one of the targets that they have. It was they stopped looking at it for a while, but then they started looking at it again. And that is an exciting star because I don't know, there might be a Dyson sphere there, right? Yeah, so might be some super advanced life there capturing energy from the star. It's probably not, but
A Dyson sphere around Bernard's star? What? No.
Let's not spread that.
yeah, let's not do that. Yeah, sorry.
Over here, folks.
Somebody once said that. I guess that's what.
Yeah,
Let me drop
Yeah,
a
we-
link
I guess
to what a
that's
Dyson.
exactly. Yeah, Freeman Dyson would be proud. Yeah.
That would be amazing. I just dropped a link to the SAO DS9, so you all can check out that
All right,
software.
I bet that would be a hot item for your viewers tonight. Man, they'll be downloading DS9 and looking at Fitz valves. Woohoo!
That's right. That's right. That's right. Okay, so I think Brian said that we're on this target for about half an hour. So if that's the case, I would love for Matthias and Brian to introduce themselves and then get a chance, since I believe that's the only two people we haven't heard from yet.
Okay. Start, Brian.
No, I'm gonna do some bookkeeping. I'll go
Hi,
after.
everybody. My name is Matias Rodriguez. I'm from Chile. And I have been here for 1 year already, working as a science operations specialist. Yeah, my job is to run telescope operations during the night and during the day. I take care of the health of the instruments when I'm slewing the telescope, and also checking the telescope subsystems. Also, sometimes I actually observed doing the job that Brian is doing now. That means that I select the different scientific programs that are on the Q plans, so we can select them regarding the weather conditions, because each observation has their own constraints. So we need to meet those constraints, otherwise we need to retake the science. Also, we do data quality assessment because of the same, checking the data that we obtain during the night. And also I'm involved in a lot of projects that are aligned with the goals of the observatory. I'm really happy because I love to work doing astronomical images here at Gemini with the data download from the archive in the case of Gemini, and other archives for Northern Lab. And yeah, that's my job here.
Thank you, Matthias. You seem to do quite a few things there, and it sounds exciting that you're on several different projects. Is there one in particular that you could tell us about really quickly?
Yeah, I think that's my favorite one. I produce astronomical images with the data that it's obtained by the observatory. And these images are published on the press releases, the web pages, social media, and helps people to understand what kind of science we are doing. And that's what I like the most, because astronomy, it's a science that it's really beautiful to see. In that sense, there you are sharing the screens. It's for me, it's beautiful. It's what motivated me to get into this world, and it converged, I think, the science, the art, and a lot of things that I really like.
Oh, yes, yes. I definitely agree, Matthias. Wow. The images are absolutely beautiful, and how exciting that you get to contribute to making these beautiful images that really help to capture the imagination of us, the public, and grab us and bring us into this amazing field. Um, and I think you said that the images was what initially maybe got you interested in astronomy. Is that right?
Yeah, that's right. I lived in La Serena, where Gemini South is. So we got pretty clear skies out there, and it's just amazing to go out and take pictures or share with your friends. So I got into astronomy by following that path, just taking telescopes and looking to the sky. It's a really nice passion that I got, and it complements really nice with my profession as an astronomer too. And yeah, I'm glad to be here, surrounded by these amazing people. Everything is an expert on their field, and I really like that. Everybody's really humble. The people that it's involved into science, into astronomy, and you always keep learning from that. That's amazing.
Absolutely, absolutely. It is amazing and it's absolutely incredible. And I know for me, one of the things that I absolutely love about astronomy is the depth and the different kinds of images that we're able to get and see. So thank you for contributing to those. And now Brian is sharing his screen. Brian, what are we looking at?
Thanks for asking, Jamaica.
Oh, that's not right. I am so sorry, Steve.
This is a great segue to something that we're going to be doing later this evening. So for people that joined the session on, what was that, Saturday, we were taking the first observations on the sky with our new mode for our Gemini near-infrared imaging spectrograph. This mode was called the High Resolution Integral Field Unit, and we were taking first images on sky with our adaptive optics system. So tonight we're going to take our first observations with that High Resolution Integral Field Unit for a science target. And unfortunately, that's going to be after the shadow session. So sorry, guys. Sorry. But our first observation with our low resolution IFU, which is the sister component to the high resolution IFU, is this observation here. And so we took an observation of two black holes that were merging in the center of a nearby galaxy. As we mentioned on the last session, I think maybe Zach talked a bit about tonight when we was talking about GMOS. So our several of our instruments here have this integral field unit capability, and an integral field unit, this particular one is called an image slicer, and it takes a spectrum of every part of the sky that it's looking at. So earlier we were looking at GMOS long slit, and we were focusing just on one target, and we put our slit down, and we got a spectrum of basically just that one target plus anything that was along one direction. Well, an IFU does that for a whole field of view. So the low resolution IFU has a field of view about 3 by 5 arc seconds. So this is an incredibly small portion of the sky, but it's enough to get the nuclear regions of nearby galaxies. And so we were able to take an observation with the low resolution IFU of these two black holes coalescing, and Mateus was the one who was able to so when we take these observations, it's all numbers. All we care about is numbers. We take the observation, it's at this location, it has this intensity at this wavelength. That's science, and that's what we use in the FITS files, and that's what we use for our data analysis. But wavelengths actually correspond to colors. Intensities correspond to different depths that our eye can see, different opacities on this image. And so we can transform. So this is not optical light. So this is not what we think of as purple to red. but it is an observation taken from shorter wavelengths, so blue type wavelengths. So in optical, blue is the shorter wavelength, all the way to longer wavelengths, which is red in the optical. And so this is a near infrared integral field unit observation. And we can see all these different features of molecular hydrogen that's surrounding these black holes. And Matthias was able to do some wonderful things to make this this data look very, very pretty and understandable for people, including myself.
Yeah, that was an amazing collaboration with Jen Miller and other SOS from Gemini and Mari Samani. It's an incredible astrophotographer. And I really like that project because it brings complex science into life. It makes it easier to understand for people that don't know what it's an IFU, an integral field of unit, which is like a cube, a 3D spectrum, slices of different wavelengths that shows the different features of this object. So you can do incredible science with these instruments. Yeah.
Yeah, so each one of these different colors is showing a different emission of molecular hydrogen. Again, I'm not like super familiar with molecular hydrogen and its emission features, but there's different energetics associated with each one of these emission lines. And so you can understand the gas by checking the relative intensities of these different emission features. And you can also, because you're getting a spectrum of every single portion of this region of this particular galaxy, you can measure the Doppler shift, so the blue shift and red shift of the light. It's the Doppler shift is like in sound, where an ambulance is passing, you're sitting in your car, as it's coming towards you, the pitch is very high. As it goes away from you, pitch drops. So that's blue shift in the first portion, red shift in the second portion, adding energy, subtracting energy. And so you can measure the blue shift and red shift of this molecular hydrogen, and you can actually get the kinematics of the gas. So as I mentioned earlier with the GMOS observation, as the gas coalesces into the central regions of the black hole can flare. All sorts of very exciting things can happen. So this is the science. This is truly the science. And these integral field speckle's awesome. I don't know anything about it, absolutely nothing about it. But of the things that I know about, I mean, like imaging, long slit, these kind of multi-object spectrograph, IFU is truly I mean, it's everything. You get everything. And if we can attach that to our adaptive optics system, which we're doing later tonight, I mean, you get the resolution of Hubble or James Webb, and you get a spectrum of every portion of the sky that you're looking at. So that's, I mean, just an overwhelming amount of information.
How long does it take to process all of that data?
Good. That's a really good question, but if we are in a rush, like in this case, it took us for like 4 or 5 days non-stop, because that image is special because it shows not only the data obtained with the IFU, but also an image made from DCAM with DCAM and Cerro Tololo that shows actually how this galaxy it's on optical light. So we produce that image using 3 filters and then reduce the data from the IFU and put that in a way to visualize it in 3D, which is that cube with the rainbow colors, and also get cutouts from slides from the brightest emissions of that object, which is the hydrogen, molecular hydrogen that you're looking on those cutouts. So it took a while because first you made each component of that image, and then you compose the whole that whole image, each component. So for us it was like 5 days nonstop, but usually
thank you, Matthias.
it's like a week for an image to be done. And yeah, and then you have this It would be great to
Yeah. And where does it go?
we share.
I can try to find it, Matthias. But yeah, so I mean, just to add to Matthias's point, like not only did it take them and 5 days of intensive work, but we have a whole department here of people called Science User Support Department that provide software that work on. So their job is to work on software to make the astronomical data that we take easier to use for the scientific community and for the public. And so an incredible amount of work by them to get a set of software that we can then pass calibrated kind of fully formed data to Matthias and his collaborators to make these wonderful pictures. So, there's this whole pipeline of people that, from the day crew to the scientists that apply to, people that are taking people that set up the observations. So Zach actually set up the plan for this evening. Then we execute. So yeah, a small portion of that pipeline is here tonight. So Zach makes the plan, we execute the observations, then the Science User Support Department helps people with their data afterwards. And then eventually science comes out of that. And that's the wonderful thing. So it's not every observatory that does all of these, has all these facets to them. We here at Gemini try really hard to allow people to use our data freely, and to anybody that's interested.
That's amazing. Absolutely amazing. Wow. 5 days to process that data and to get some of these beautiful images that we're used to. I can't imagine what it takes how long it takes to analyze data from like Hubble or JWST and come up with those beautiful images, like the comparison with the pillars of creation with Hubble and then the JWST's image of those. Do you have any sense of how long it takes to reduce data from JWST? And I think Brian, you maybe others also have JWST time.
Well, the question is reduce it or reduce it well. You can reduce. You can make pretty pictures, and that's great, and they're beautiful. They're absolutely beautiful, and they excite the imagination, and of course they're a necessary part of the process. But if you're doing science with the data, you want to. They're only as good as your calibration, and so if you can do a quick and dirty calibration, and it can give some science and a lot of very exciting JWST results. And when Hubble was getting upgraded, the Wide Field Camera 3, there was a lot of excitement around. Okay, here's the first images, and everybody's giddy, and they're oh my gosh, there's this thing. But then when you start to take a bit more sober look, you start to see, okay, so actually I need to do slightly better calibration here, slightly better calibration here. That bad calibration led to some kind of funny results. And so there's a maturation process with every new instrument, with every new observatory that comes online. People get very excited. You make these pretty pictures, you get out some quick science, and it drives the science forward. That's for sure. Drives in the wrong direction sometimes, off a cliff sometimes. It pushes us all forward to do better. And one of the wonderful things about science is that people then litigate back and forth. They say, hey, no, your reduction's no good. Mine's the best. No, yours is not. And there's that kind of healthy competition to make the science better. So, I have a what's called a medium-sized program on Hubble that I've had for 2 years now. It's taken 2 years to get the observations. We have 50 what's called orbits. So each orbit is about 50 minutes, but it's spread out over the course of many years. We're still trying to reduce those data. So after 2 years, these are called GRISM observations. They're very, very complicated to reduce. And it's been 2 years that me and my team have been trying to reduce them in a way that we're satisfied with. And we're just now making headway that we feel, comfortable to start doing our science. So it can take a very long time.
Wow. 2 years and you're still going.
Yep, still
What about with Alopeke data and Zorro data? Steve and Nick, is it when you're reducing the data from Alopeke and Zorro, what's that time frame, that turnaround like?
You're the last person to reduce some of the
Yeah, so a lot of our data is a lot simpler than this. So that's a starting point. So each of our observations might last 10 or 15 minutes. And our reduction of that particular observation might be about 15 to 30 minutes. So each observation for us doesn't take very long. Where we get into trouble in time is that we might take 100 observations a night times 5 or 6 nights in a row. So the total amount of data and then the total amount of time lasts for a long time. So it just depends on the data sets and how they work. And some things are simpler, but you can take more of them and then it ends up being more complicated in length. So
we're taking that 60 milliseconds works out to like 16 to 17 frames per second. So we're taking data at movie film rates. And then depending on which mode we're running the cameras in, it could be up to like a gig per file. Most are smaller, we crop down and just look at a small region because of that, but terabytes of data are commonly used.
And so what about students who are using this data? Terabytes of data is really challenging for the regular laptop to process in any kind of reasonable time frame. What do they do?
well, the good news is computers are pretty fast these days, and students don't sleep much if they work for us. So we eventually get a lot of things done, and in the end, those terabytes come out to much smaller, manageable parts. So our program really uses the term data reduction in a real way.
Oh, I hadn't thought about it like that. Data reduction. Got it. Nice, Steve.
Of things running so quickly, we've had there's been I've heard friendly competitions between Gemini North and Gemini South operators to see who could get more Alopeke and Zorro targets in a night.
Well, that sounds fun.
Yeah.
Nice friendly competition.
Competition?
Maybe the other day I saw a night like with a crazy night log full of Alopeke targets. I think it was Emma operating. I don't know who was it.
Emma and Charlie.
Emma and Charlie? Okay.
Many operators don't like to work when Alopeke or Zorro are on because we switch targets pretty quickly. And we also I think you have to take that contest and divide by dark hours because Gemini South in the middle of its winter, it's some long nights. And so you can really, you can be very tired. Yeah, so you might have to rate it by the hour.
Yeah, we're gonna move on. So 222-32, please.
All right. So we have a question in the chat. Zach, it's from Nandini. Thank you, Nandini, for your question. Says the black hole spits out some stellar material back into space. Can we capture that phenomena and calibrate it to get a hold of the actual source that went into the hole? Good question to all in the control room.
I'm going to turn this over to Brian because it is not my field, and at least it is at least near to what Brian works on.
Sorry, what was the question? Do you mind repeating, Jamika? I think you're muted. Oh, I can actually look at the
I'm so sorry about that. Yes. So black holes, we're going back to black holes. Black holes spit out stellar material back into space. Can we capture that phenomena and then calibrate it to try to get a hold of the official source that went into the black hole originally?
Okay, so the black hole is not actually spitting out any material. It's accreting material, and that material heats up as it falls into the black hole. And so what you see around a black hole that's active is a lot of very hot gas. Around the central regions of our galaxy, you will see what's called violent disruption events, I think, or violent disruption events. So you'll see stars that are kind of that can be ripped apart, but mostly there's just stars that are kind of wandering around the black hole aimlessly. So they're basically gravitationally bound to the black hole, but so they're whistling in the dark. And if they interact tidally, so if two stars happen to move past each other, their orbits are disrupted. They can fall into the black hole, and the material would heat up, and we would see the result of that. So we would see the emission coming from that hot gas. But once some material enters into the event horizon of the black hole, which is the boundary at which light can't escape, that information, as far as we know, is basically lost to us. There is a way for black holes to radiate back out that information. It's called Hawking radiation. But basically all the information is lost at that point. So the information is during the infall process. It's not after something enters into the black hole. That's pretty much it. One of my favorite facts about a black hole is that if you fall into a black hole, the more you struggle, the faster you get to the center. So if you ever happen to fall into a black hole, just relax and enjoy the ride.
Like quicksand.
Yep.
Wait, Brian, why is that? Why is it that if we struggle as we're going into a black hole, that we would get there faster than if we didn't?
So the gravitational pull is so strong that actually everything will move you in the direction of the black hole. So sorry, what?
You're not on camera.
Okay. So yeah, everything will every movement that you make will basically just push you closer towards the center. Sorry, I have to get back to the observations, but just don't get captured by a black hole. That's the rule.
Hey, that's the advice.
Yeah, that's a good advice.
That's perfect. Thank
Can you do a P offset of 4 and a Q of 1, please?
Yeah, one of the things that we're starting to get Alopeke to do is look at extragalactic stuff. So hopefully that will keep going. What?
The results of your proposal?
No. We'll know in I don't know, a week.
A week. Good luck. That's great.
But
Matthias, you put in 20, I think.
we've taken
Minus
minus
16
images of binary quasar pair, very faintest object we've looked at with Alopeke,
P plus 4.
and hopefully expanding into more. So
It's the one at the side. Sorry.
Oh, that's good.
That's like binary stars, binary black holes teach you a lot about black holes. You can learn a lot more about black holes if you have two of them.
Can you do a Q plus 1, please?
Everything binary is good.
This is
Thank
such
you.
a great conversation, and I am grateful for for everyone's contributions. This has been such a dynamic session, and I can't believe we only have 16 minutes left. I'm looking at Zach's screen. Zach, what's going on there? I believe we're still on the last target, which is a maroon. We're using MAROON-X, and we're at this on this same target for about half an hour. And for
we've actually moved to a new target. So Brian and Matthias are in the process of acquiring this target. I think they have.
Yep.
And
Just we're starting 5-minute science.
Started a 5-minute observation. So we're here for 5 minutes, and then we go to something completely different.
All of a sudden, I feel like we're on a telethon.
where you guys are definitely stars. How about that? You're definitely stars.
Oh,
thank you.
Oh, shucks.
My goodness. I definitely would like to make sure those who are joining us in the chat have the opportunity to ask us questions. Miss Peggy Lamo has left the session so she could get back to her research. She's
You got bored.
get
I
back
think
to
she had to get it.
All right, well, I challenge your viewers to ask us a question we can't answer. So.
Ooh, okay. So, all right, those of you who are joining us in the chat, a question that they can't answer.
Somewhat related to astronomy.
Yeah, that's a good qualifier. Yeah.
That was good. That was good. Yes. And while we're waiting for that awesome question that related to astronomy to stomp our group of researchers here, I'd like to take it back to Andrew. Andrew, so to be a part of the day crew, and you mentioned that there are a wide range of specialists who make up the day crew. What kind of educational background is required?
Oh, that is a very interesting question. It really depends on the position. So if you're with instrumentation, yes, you're going to need quite a bit of extensive background on electronics, and cryogenic systems, vacuum systems is very desirable. They don't have schooling for observatory. They just don't. So, we have a lot of people who come from building motorcycles, people who worked on drones for the military. I have a guy who is like my electrician. He worked in a fish cannery in Juneau, Alaska. People who just all walks of life who are just passionate about working up on the mountain. They just make it work, you know. But they all bring something to the table, because it's all hydraulics, it's all pneumatics, it's all metalworking. You know, even the people who work on the chemistry and the glass, you know, they come from, yes, optical backgrounds, but just whole different myriad of fields that just kind of mesh together, and we all do the same goal. Like even myself, I don't have a science background at all, but I'm, you know, managing everybody here and trying to just make this observatory work every day, every night. Yeah, no, we're all very eclectic in our backgrounds. Yeah,
I'll add on to that, because you hit on one of my favorite things about astronomy.
Yeah,
is that to do astronomy, you need to have optical engineering, mechanical engineering, electrical engineering, and then the subsystems of hydraulics and vacuum systems and all of that. And all of it is like, has to work perfectly to move hundreds of tons smoothly
yes.
to a ridiculous degree to keep the mirror aligned and focused to a fraction of a wavelength of light. Like, it's just, it shouldn't work.
It should not. Yeah. And you think it takes like somebody with like 5 PhDs and 3 masters to do it, but if you're passionate,
Cumulatively, we have.
yeah, cumulatively. No, we have a very supportive team, people who are very passionate and eager to get the work done. It just works out, you know. Yeah.
Yeah, I like your point about there's no school for
There's no
observatory.
school for
Yeah,
it.
if you want to work in heating or air conditioning, there's 8 billion homes in the world that have heating and air conditioning. So there's tons of people that train you to do heating and air conditioning. And if you want to work on putting roofs on houses, there's tons of places you can learn it, because there's lots of roofs on houses. Not a lot of observatories in the world.
No.
So not a big market for educating people in observatory work.
I really dislike it when HR puts out a recruitment post. Past observatory experience. It's like, no, wrong. Stop it.
All two of you.
Yeah, all 2 of you. Yeah, you're not gonna find this unicorn person. Just doesn't exist.
Yeah, I think many people in all aspects of astronomy have a passion for their work. And that seems to be the common goal or the common characteristic across whatever they do.
Yeah.
Right? There's not a lot of money.
I was gonna say, yeah, we don't get paid well enough.
Not a lot of money.
I was in it for the fame and the glamour.
Yeah, not a lot of prestige, not a lot of whatever, and so it's just people have the passion to do it.
I mean, the day crew has a very interesting perspective because we get to be inspired by astronomy. We don't have to be in the data or the science. We don't have to do any of the dirty work. We just enjoy the end results. Yeah, the pictures. So when you guys do science highlights, so we have no idea what it took to get to that, but it's very nice. Yeah.
I think it goes both ways, because I know
Yeah.
quite a few scientists that don't appreciate the amount of work that goes into
Oh,
making
yeah.
a telescope actually run
Most of it.
reliably. There's like, no, just push the button.
It's an extremely challenging environment out there when you're working freezing temperatures with not as much oxygen, and you're trying to lift up like 50-pound metal plates. It's
Well, even like specs of electronics, like every electronic you buy, like you buy a toaster, it says, you know, it's good for 0 degrees to some temperature, high temperature. Getting electronics, like the computers that we're putting on Alopeke, they're not rated to go below freezing. They will be below freezing.
Not rated for high altitude.
Not rated
Will
for
be at high
altitude, you can't get ratings for altitude, and these things have effects.
even when we're trying to service any kind of equipment, we can't even get the technicians to come up who built the thing. They come up to the mountain and it's like, oh, well, you're up 14,000 feet. Our warranty doesn't cover anything.
Yep.
Well, that's wonderful.
What do you do in that situation, Andrew? Do you talk with them on the phone and then you all troubleshoot on your own with their guidance?
Well, the great thing about NORLab is that we're not existing in a bubble. We can ping other observatories, ping other experts. I got people in Chile that I can reach out to and, oh yeah, we had that exact same problem as well. And this is what we did to fix it. So it actually really helps having an exact copy of our facility. And so all the problems that they have, I can just ask them like, hey, how did you fix that? We're also trying to work with some vendors who understand our challenges, because when we were built, I kind of feel like a lot of the equipment was kind of boutiqued as this is standalone, this is one of a kind, and good luck 30 years later trying to find someone who knows how to fix it. So we're having a lot. We're reaching out to a lot of vendors who are willing to work with us a lot better now because they also have worked with some observatories like Toshiba, and some Vertitech is another good one for aerial lifts. So yeah, the industry is changing always, you know, so it helps.
I really like NIST as an instrument because it was built using already proven methods. There's nothing really great, like stupendously new about it,
Right.
but it just works and it works really well.
It's the Volvo of instruments.
Right, and it's like the same thing with Alopeke and Zorro, where they're built on already established techniques, and the only thing that had to change was now you had to fit it into the size of a suitcase and fit it into the.
It's all
fit it into
commercial,
there.
all of Alopeke and Zorro are commercial off-the-shelf equipment.
None of which should work in Maunakea, but.
Wait, I'm sorry. Did you say that the equipment is off the shelf that you use for Alopeke and Zorro?
Yeah.
Radio Shack?
If only. Yeah. Yeah, so they're all commercially available parts. They were just put together and then used in a way that wasn't commercially done because how many people have their own speckle camera?
Yeah, in the filters.
Yeah.
There's no.
And then the mathematics is all custom stuff that we've developed over it.
Getting at 100.
100, thanks.
And Tamika, tell you, like, how many people do you know have a cell phone?
Everyone.
How many people do you know have a NIRI
Yeah.
or a GMOS?
Just y'all. Just y'all. No one else.
Yeah, so almost everything astronomers do is one.
Yes. Incredible. What fantastic insights y'all have been sharing with us. And we're down to the last 5 minutes of the session. So before we wrap, get to the end, I'd like to.
Big question.
Was that, yeah, let's get back to a question here from Sam. And this is for everyone in the control room. Can you pass the event horizon of a black hole? So can you pass it. And
Yeah.
so you can't. Well, okay, so here's the next part of the question from Sam. Or do you get launched into the future as Hawking radiation due to the extreme space-time curvature? Thank you for this question, Sam.
Right?
I can't multitask. Not gonna start right now. I'll let you guys take it.
That's hidden philosophy of what you are, because what's coming out as Hawking radiation is not your
It's there.
consciousness anymore. It's just high energy particles.
It's just energy now. Well, no one's ever done it to let us know, so.
That's a good point. That's a good point. That's a good point. Right, exactly. And so maybe could we talk a little bit about the Chandrasekhar limit?
Sure.
And I got a question, a direct question about that. And then the how close can you get to an event horizon?
Depends on how powerful your rocket is, right? Like the event horizon is defined based on the speed of light, but with like a conventional modern rocket that we have now, we couldn't get anywhere near the event horizon and still be able to get away because we can't go. It's whatever percentage of the speed of light we can go.
Yeah, take it 30 minutes then.
Also, as you get close to the event horizon, you get really stretched out. You know, you have a rocket, the gravitational pull on one end of the rocket is just tremendously different than the gravitational pull on the other end of the rocket. So things get stressed out, ripped apart.
You get weird tidal forces. There's a sci-fi short story about that. Arthur C. Clarke did, or it was Isaac Asimov did a short story where it was like a murder mystery in a rocket where the people at the front end and the back end of the rocket were horribly killed, and the person in the middle was okay. And it's because they had slungshot around a black hole, and the tidal forces in the middle were okay, but at the ends had just spaghettified the people.
Oh wow! I don't think I read that. If you think of the title in the next 3 minutes, let me know.
No idea. It's in one of his collection of short stories, I think.
I'll check it out. I'll check it out, Nick. Thank you. Okay, more questions. Thank you. This is from Nandini, and this is to everyone in the control room. Was there existence of time before the Big Bang? And what kind of force initiated it all? Simple questions. I know you got it.
None of us are cosmologists.
That's a good question.
The favorite way I've heard that described is that before Big Bang, there wasn't time because there's some cosmologists that argue that it's the expansion of the universe that creates the illusion of time, and that we define time based on the direction of entropy. And so then there is the idea of before Big Bang makes no sense because time was also one of the things created in the Big Bang.
Yeah,
But
there's also the idea that before the Big Bang, there could have been all sorts of things, but none of that knowledge is ever transferred to this side of the Big Bang. So we'll never know what was before if there was a before.
Yeah. Or if there were multiple Big Bangs and there's multiple universes, those are completely isolated from ours. And so does time carry on outside of that, or do we have our own time?
But great question.
Yep.
Something you should work on for a PhD thesis.
Yes, these are fantastic questions. Fantastic. And thank you all for your for the responses that you gave to it. Yes. Thank you so much for that. Nandini, I hope that was answered your questions. And if not, shoot me another follow-up if we need clarification. So in the last 2 minutes, I'm going to give it back to Zach. Zach, we have 2 minutes left. Maybe can you wrap up for us what you are going to be doing in the rest of the evening's observations, more with the different instruments you're going to be using, the science, and maybe we can wrap up with a look at the weather, because I think it's a gorgeous night.
It is a really good night. I'll put that up as I talk. There we go. So it's going to be MAROON-X for a little bit of the night. But then, depending on conditions, we will be switching conceivably to Genius, or we do more MAROON-X.
No, we're switching engineers.
You said WV50, and I don't know what the WV is. I don't know what the water vapor is.
It's
Yeah, you haven't even looked at it.
No, I haven't.
So depending on that, we may be doing Genius, we may do the MAROON-X, and then at the end of the night, there's big long GMOS transit. You have conditions.
Yeah, it's the IFU one, right?
What?
It's the IFU one.
I believe so.
Yeah, yeah. You were very kind to us today.
Yeah, it gave you a nice long.
Yeah, so yeah, we had a what 4-hour one last night, something like that, and we had another 4
hours.
4.5, and we have another 4 hours tonight. So yeah, so yeah, I think we'll if the conditions are as nice as last night, which they were absolutely insanely good last night, and they're pretty comparable tonight. Yeah, then we'll be rolling. Everything's fine. So yeah, so we have about 20 minutes more on this MAROON-X target, and then Zach was kind enough to schedule us for doing Genius high resolution IFU observations next. So that's our first light for science for that mode for the observatory. That's very exciting. That's 2 years coming. So we've been working on this for 2 years. Just at Gemini, we've been working on it for 2 years. Prior to that, about 5 years in development. So 7 years in the making, roughly. This is the instrument builders are in Durham, the same team that built the integral field unit for James Webb, for example. So they're very good at what they do. And now we're going to showcase its amazing capability. So yeah, so if you come on future Gemini North Shadow of the Scientists sessions, we should have that all commissioned, and we should start doing like real life science with that. That would be fun. And then yeah, so and then the observation that Zach mentioned, which is the a GMOS integral field unit observation. That's part of the capability of GMOS already, and that observation will be of what's called a post-starburst galaxy. So a galaxy that it has rapidly declined in the number of stars that are forming. So probably it was something like the Milky Way, or a little bit more vigorous than the Milky Way in terms of forming stars, maybe 1 or 2 sun-like stars per year. And then all of a sudden something happened, something weird happened, and it just stopped forming stars. And we don't know why. And so we'll take an observation across the entire galaxy. We'll get a spectrum at every single location. And what the supposition is, there are shocks that happen in these galaxies and have somehow shocked the star formation, heat up the gas so that stars could no longer form. And so that observation is to determine whether that supposition is correct or not. So all sorts of fun things.
Wow, I'm definitely excited to catch up with you all next semester. And also next month in January, which is also semester 24A. And I do believe we can expect some Gemini sessions in January, Brian?
Yeah, so that'll be the very end of 23B. So I think we shift over to 24A just at the end of that month. And yeah, so I think we're going to do one somewhere around January 15th or so. So a little more than a month. We'll be back here, and who knows what we'll be looking at. It could be anything. Could be anything. And then we also have in 10 days, my research group will be on Keck for 2 half nights. And so we'll have crazy late night shadow scientist sessions then as well.
Absolutely. So you will be able to find registration links for the sessions with Brian's research group here tomorrow. So please sign up for that if you get a chance to. And thank you all for joining us. We have some comments in the chat. Yuli says, having all y'all in the control room really made the session lively. The fun and banter plus science would really appeal to her little ones, her students. Thank you so much for that feedback, Yuli, and you will definitely get an email from me to follow up and schedule a session for your students. We also have from Marufa. It's so good to have you in this session, Marufa. Mahalo for an amazing session. It was fun. And from Rob, we're always so excited to have you. Thanks for a lively and informative session. Yes. Thank you so much, everyone, for joining us. Just to reiterate the words that Zach has in the chat. This was absolutely amazing. So much fun, so much energy. Steve, Nick, Andrew, Mateus, Brian, Zach, and I think I absolutely forgot to introduce one person on the couch. Is that Cicero?
She snuck in here trying to hide.
Like the last 5 minutes, you know.
Oh my gosh, I apologize, Cicero. I just saw you like 10 minutes ago. If you'd like to introduce yourself, we would love for you to do so. Cicero was in our previous session on Saturday, and we hope to have her in future sessions.
Thanks for kindly having me. Sorry, I was trying to be sneaky, but your eyes are too good. So my name is Cicero Liu. Sorry, I haven't been involved in the past 2 hours or so. I'm also a science fellow, but working on a slightly different type of team at Zach. So I'm involved in MAROON-X, which is the main instrument, one of the big instruments that we're using tonight. I'm also helping with junior science. So very hoping this will happen later tonight. And I'm also on the fast turnaround team here at and currently I'm training for night shift people. Congratulations on another wonderful night of STS.
Thank you, Cicero, for that introduction, and thank you all for allowing us to shadow you, for opening the virtual observatory doors to allow us to shadow you and join you for these 2 hours of observations. So everyone, we look forward to having you in future sessions, not only those January sessions coming up for Gemini North, but also Brian's sessions coming up in just a few weeks. I really would love to thank you all, especially Zach. Zach and Brian, you all really have actually made these sessions possible. Without your passion, your enthusiasm, all of your support, we wouldn't be here this evening. So thank you so much for that. Steve, Nick, Cicero, Andrew, Mateus, it was a pleasure to join you, and we look forward to next semester's sessions.
Right back at you, Jamaica.
Yeah, Jamaica, you're really being the heart and soul of this, so.
Y'all are amazing. I appreciate you so much, and we will see you in the next Shadow the Scientist session. Have a good rest of the evening. Aloha.
All right, thanks everybody. Aloha.